Hi, welcome back. This is Lecture 2 in the Energy and Sustainability course. Today we're going to be talking about thermodynamics, the laws of thermodynamics and sustainability. Thermodynamics is, the laws of thermodynamics are some of the most fundamental and again, this mysterious quality of energy, mysterious laws in the universe. There are 4 of them. And we're really going to be concerned mostly with the first and second law of thermodynamics. So the first law of thermodynamics, which we talked about in the lecture on energy physics, states that energy is neither created nor destroyed. It eternally flows in transformation from one form to another. So you might think that if sustainability depends on having a source of energy, then this is good news because we have all the energy we ever need. We have all the energy we ever have had. We have all the energy we ever will have in the future. And it just transforms from one form to the other. But there's a pesky second law of thermodynamics. And we're going to get into more detail in all these, but I wanted to lay this out right here at the beginning. And the second law of thermodynamics says every time that energy is transformed, some of its usefulness is lost. And it's lost in a particular way. Energy transforms in a particular way. It goes from being concentrated to being diffuse. So to give you an example, like we talked about in the last class, if I take a cup of hot coffee and I put it on the table, it's eventually going to get cold. It's never going to get hotter than it did when I put it on the table, unless I put energy into it. So energy always transforms in this particular direction. Air always leaks out of the tire in your car. It never leaks back in. So the second law of thermodynamics has huge consequences for day-to-day life and for life in general across the universe. And because of this tendency of energy to disperse, to go from being concentrated to diffuse, if we want to continually regenerate the usefulness of nature and the usefulness of society, the usefulness of nature to society, we need to have a source of energy that offsets this lost usefulness. Now we can offset the lost usefulness by bringing more energy in. And in the big picture, solar energy, the inflow of solar energy, is what creates that order and structure which overcomes that lost usefulness due to the second law of thermodynamics. It's done by plants. Plants take solar energy and create complex carbohydrates, which then are the basis for the order and structure of all the beautiful biological activity we see all over the planet. So again, energy in the second law fundamental of thermodynamics operates at a very fundamental level. And that solar energy is really of primary importance to both nature and in the economy of people, because we need to offset the effects of entropy. So that's just a really brief overview. I mean, we'll get into the details of this in this lecture. So thermodynamics really is about how infinity is expressed within the boundaries, how creation manifests. It's why anything happens in creation in the universe. And one way you can think about it is how that abstract quality of intelligence becomes intelligent, becomes focused in a particular direction in a particular way. And thermodynamics helps to explain how that happens. So here's C.P. Snow, and he was famous kind of scientist and philosopher. He helped establish the field of the philosophy of science. And he, in 1959, he put out a very influential lecture called The Two Cultures in the Scientific Revolution. And here he saw that there were two kind of a humanities culture and a science culture that were developing in different directions, and he thought that was kind of a problem for our society to not have those two cultures be able to talk to each other. So he again points out the key role that the second law of thermodynamics plays, and I'll just read this quote. "A good many times I have been present at gatherings of people who, by the standards of the traditional culture, are thought highly educated, and who have the considerable gusto, and have with considerable gusto been expressing their incredulity at the illiteracy of scientists. Once or twice I have been provoked, and I have asked the company how many of them could describe the second law of thermodynamics. The response was cold. It was also negative. Yet I was asking something which is the scientific equivalent of have you read a work of Shakespeare? And then from Albert Einstein, he said, a theory is the more impressive, the greater the simplicity of its premises, the more different kinds of things it relates, and the more extended its areas of applicability. Therefore, the deep impression that classical thermodynamics made upon me. It is the only physical theory of universal content that I am convinced will never be overthrown within the framework of applicability of its basic concepts. So, both C.P. Snow and Albert Einstein are arguing that this is a central. This should be something that any educated person understands. This law of thermodynamics, and it's one of the most fundamental laws in all of nature. So, let's talk about all the laws of thermodynamics. Really, we're going to be concerned about the first and second law, but the first, second, and third law of thermodynamics were kind of developed first during the 1800s when people were working to understand the flow of heat. That's why it's called thermodynamics, but really applies to a lot of different kinds of energy flow. And when they got done with the first, second, third laws, they realized, there's one other law that's kind of fundamental and underlies all these things. So they called it the Zeroth Law of Thermodynamics. And that just says when two systems are in thermal equilibrium with a third body, like a thermometer, they are also in thermal equilibrium with each other. Therefore, these bodies are all at the same temperature. Now, this law allows us to define temperature scales in thermometers. It says if you take a thermometer and put it in one liquid, let's say, and it becomes at the same temperature as that liquid, and you move it to another one, and it's also at the same temperature, the two things are in equilibrium with each other. So the first law of thermodynamics, which we've talked about quite a bit before, it says energy is neither created nor destroyed, it's eternally transformed. So we've talked about that. And then, the Vedic science point here is being is the silent source of all creation, destruction, and maintenance. So energy, again, is at the core of any time any change takes place in the universe. Just like being underlies all the various fields of activity in the universe. Now, this so that's the first law. Now, the second law of thermodynamics, here's something I pulled off the inner little conversation, the question and answer. It says, who cares about the second law of thermodynamics? It's anyone who wonders about the material world, our world of matter and energy, how it works. Is it a big deal? It's the biggest, most powerful, most general idea in all of science. It's why paper, trees, coal, gas, and all things like them burn, and why people should spontaneously catch fire in air. It's why sand and dry ice, even in pure oxygen, can't ever burn, why the sun will eventually cool down, why iron rusts, why there are hurricanes or any weather at all on Earth, what makes things break, why houses get torn apart in tornadoes or explosions, and why every living thing tends to die. That's just for starters. And it also, because there's this tendency of things to go from being more concentrated to dispersed, to go from a concentrated form to more dispersed form, it gives a direction to time in a way. If you think about it, a plate will break, but it will never unbreak. A diver will dive off a diving board, but he'll never undive off a diving board. He'll never bounce up out of the water back up onto the diving board in the reverse direction. And so this kind of gives a direction to time, actually. And so that's another one of these mysterious qualities of energy in the second law of thermodynamics. So again, let's try to state the second law of thermodynamics in a couple of different ways. One is that energy spontaneously tends to flow from being concentrated in one place to being diffused or dispersed and spread out. So energy on its own will flow from being concentrated in one place to being diffused or dispersed and spread out. It doesn't flow the other way on its own. All physical processes proceed in such a way that the availability of the energy involved decreases. Now, the quantity of energy will not decrease, because we talked about that in the, when we talked about the first law, that we have the same amount of energy, but its usefulness or availability of that energy to do something decreases. That happens. That's just an inevitable consequence of how physical processes work. Another way to state the second law of thermodynamics: unless you deliberately move heat by doing work on a system, heat always flows from hot to cold. So another consequence of this, there's many different consequences of the second law of thermodynamics, but in all energy transformations, some usefulness of energy is lost. And this loss of usefulness, we call it entropy. It has a term in physics called entropy. So energy cannot be created or destroyed, but entropy can. Things can become more dispersed, or they can become concentrated. But in order to become concentrated, it requires energy from outside the system. So here's an example of, if we look on the left side here where I'm showing the cursor, we've got two pressure reservoirs. One has a higher pressure than the other. You can see the gauge here. One's at about 100 pounds and one's at about 0. And so there's a valve here between them. If I open the valve, what's going to happen? The high pressure air is going to flow into the low pressure side, and then they'll become equal. Eventually the two sides will become equal. And you can see that in this third picture. And so when you open this valve, air would never flow from the low pressure to the higher pressure side. It just would not happen. Now you can think of, well, maybe I could make a little machine here in this diagram where I take the flowing air and I put it into a little turbine, and I collect and save that energy, and then I can use it to move air back the other way again. But that won't work, because what happens when you transform the energy from the energy in the flowing air to the turbine, some of its usefulness is going to be lost. There's inevitably going to be loss of ability to do work, and you will never be able to put the air back into the other side. So a couple of implications of the second law. It means that you can have no 100% efficient energy transfer, and that unless you add energy, things are not reversible. In other words, you can't go in one direction and have energy become more diverse, and then, or system become more dispersed, and then have it go back the other way without putting energy into the system. It also has implications, interesting implications on the efficiency of thermal power systems, and I'm going to show you in a little bit that the efficiency of a thermal power system has an inherent fundamental physical limit that you can't get around, no matter what kind of special materials you use or what kind of special fluids you use in the system, thermal power system. You can't get around this maximum efficiency. And we'll find that in many of the energy conversion systems, renewable energy conversion systems, there are fundamental physical limits on the maximum efficiency. For example, with wind generators and for thermal power plants. And those are related to the second law of thermodynamics. We'll talk a little bit more about this. Again, entropy is lost ability to do work. You still have the same amount of energy, but it cannot do the same kinds of work anymore. So again, when we use this example of a cup of coffee, it's going to get cooler when you put it on the table and not hotter, unless you deliberately do work on the system, unless you put heat underneath it with some source of energy like an electric element or something like that. Then it'll get warmer, but it won't get warmer on its own. Another way of looking at this, another consideration here is with chemical energy. So there are chemical energy stored in the bonds of chemical bonds of different materials. And so we have paper plus oxygen. It's up here at this high level. But if we combine it and burn it, the energy actually is down here at this lower level. You get CO2 and water. You get paper and oxygen, which is kind of a more orderly, you can think of it a more orderly, a more concentrated form of energy. And then if you burn it, you'll get carbon dioxide and water, and it's at this low level. So what the second law of thermodynamics says is this reaction will tend to happen spontaneously. Now, why doesn't it just happen all on its own? Because there's something called activation energy. If we look here on this graph, that we start out, we have to actually put a little bit of energy in. We have to strike a match. We have to add just a little bit of energy. But once we put that little bit of activation energy in, the reaction will occur on its own. It's like if you have a marble, or think of it of a ball rolling down a hill, and it can get stuck in a little depression. Even though the overall slope is downhill, there's a little depression. It gets stuck there, and it'll be stable, and it'll stay there until you actually push it out. And activation energy is a good thing, except if it wasn't for activation energy, everything would spontaneously burn up in the oxygen of the Earth's atmosphere. So activation energies protect substances from change. So that this is also something that's in consideration, particularly in chemical systems. So so when we look at the implications for the second law of thermodynamics, this idea that everything tends to go from more concentrated to dispersed, from more useful to less useful, that has some consequences for sustainability. If we look at the conventional ways of thinking about sustainability, typically efforts in efficiency and substitution, how do we become do the processes and systems that we deal with in our daily life using less energy and less materials? That's efficiency. And substitution is how do we take and substitute the toxic materials and processes like fossil fuels and harsh chemicals for non-toxic energy and materials and processes like renewable energy, substituting renewable energy for fossil fuels, or non-toxic materials for toxic materials. So that's one level of sustainability, but it doesn't say anything about, are you giving back for the future? Are you able to offset those inevitable effects of entropy? And deep sustainability says that we're going to design systems not just for efficiency and substitution, but for regeneration and renewal. We're going to have to offset the effects of entropy. We're going to have to leave opportunities for future generations. And the way we need to do that is with solar energy. Solar energy is really the only form of energy we have that's renewed on a daily basis. Energy doesn't cycle. It flows from a high-quality source to a low-quality sink to a point where it's no longer available for use in the system. And so in order to have sustainability, we have to have a continuing source of high-quality energy to offset the effects of entropy. We've been using fossil fuels for that, which is ancient stored solar energy, but we need to learn to use solar energy directly in order to have deep sustainability or have long-term lasting sustainability. And the human mind and spirit and body have their own laws of entropy. We get tired, we get worn out, and we need to be refreshed. And TM offsets the entropy in our individual lives, and also in the group practice of TM offsets entropy in the collective consciousness, therefore supporting regeneration and renewal of the individual and of the entire society. So let me give you another example of where this understanding of the second law of thermodynamics can lead to surprising results. James Lovelock, he's a pioneer in the sustainability movement. He was one of the first people to understand what was happening with how aerosols were destroying the ozone hole. He discovered that the ozone layer on the Earth's atmosphere was diminishing and disappearing, which causes increased high energy ultraviolet rays from the sun to come in and cause skin cancer and other kind of cancers in living creatures, health problems for living creatures. And so he's an expert on kind of atmospheric physics and all those kinds of things. And his research in these areas led him to think about why is it that the Earth's atmosphere stays at a very stable chemical concentration, very stable temperatures over very long periods of time. And he came to the conclusion that the living systems on the Earth work together in harmony to create the conditions for life, to create and maintain the conditions for your life. It's like your body stays at 98.6. It has self-regulating mechanisms that do that. And he discovered that the Earth has a number of these, and he threw out an idea that the Earth is like, in some ways, a living being. He didn't quite go that far, but people have gone that far and said, okay, we're just subsystems on this larger living being of the Earth, and he called it the Gaia hypothesis, and you might have heard this term Gaia. And one time he was asked by NASA, can you design instruments to tell us whether there's any life on Mars? And we're going to send them to Mars, and you're an expert on the gases in the atmosphere and various things like that. He said, I can tell you by looking at Mars and analyzing the composition of the gases of Mars' atmosphere from the Earth that there's no life on Mars, because all of the chemical reactions have gone to their ultimate end conclusion. Entropy has set in. There's no systems on Mars that are far from equilibrium. Like on the Earth, an atmosphere with 20% oxygen is highly unlikely to be maintained, because everything oxidizes, all kinds of things, rust, iron oxidizes to rust, things burn. And so in the absence of life continually regenerating and renewing that oxygen in the atmosphere, it would quickly go to its thermodynamic equilibrium. And so he said on Earth, many things are far from thermodynamic equilibrium because life is creating order and structure. It's offsetting those effects of entropy through the use of solar energy. And if there was life on Mars, it would be doing the same thing. I don't see that, so there's no life on Mars. And that was his, again, using that second law of thermodynamics in kind of an unusual way. Let's look a little bit about that solar energy that creates that kind of order and structure, biological order and structure on the planet that we all depend on. Let's look at where that comes from. So it comes from the sun. It hits the Earth's atmosphere, and about 6% of it is reflected back into the atmosphere. 20% is reflected by clouds. 4% is reflected from the Earth's surface. So right off the bat, about 30% is reflected back. And then some is absorbed into the atmosphere, which warms the atmosphere. Some is absorbed by clouds, which warm the clouds. And about 51% is absorbed by the land and ocean, which warm the land and ocean. Now, what happens to all that energy? We know that energy is neither created nor destroyed. So it turns out that all of that energy eventually reflects back out into space. And it's radiated from rising air, conduction from the ground to the air, radiation that is radiated directly from space because the temperature of the Earth is higher than the temperature of space, and radiated to space from clouds in the atmosphere. So all of the energy that eventually that comes into the Earth eventually goes back out into space. And the sun drives the hydrological cycle. It drives the evaporation of water off the land and off the oceans, and then that comes back and falls as rain, and that cycle's been going on for billions and billions of years. Connects everything on the Earth in the past and present and future. Some of the water in your blood was once in the blood of dinosaurs. Some of the water in your blood was once in all the great rivers, the Ganges, the Mississippi, the Nile, the Amazon. Some of the molecules of water in your blood once flowed in all those rivers because we're connected by this water cycle, powered by solar energy. So a source of high-quality energy must be continually introduced into a system to offset the effects of entropy to create order and structure. Solar energy provides this for Earth. And in the human body, the regular experience of the silence of being offsets the effect of entropy on the physiology and mind. So let's take a look at how a coal plant operates. And this, I could do the same. Solar thermal electric plants operate this way. Nuclear power plants operate this way. Gas-fired power plants operate this way. Biomass-fired thermoelectric power plants operate this way. So you have something. You have a boiler here which has water in it, and you have fuel and air which you burn to create heat. That heat boils the water. The steam, the water turns into steam, expands, and creates a lot of pressure. That pressure is run through a turbine which spins a generator, which makes electricity. Now, the steam comes out and it's condensed, and you take heat out of it, condense it back into water, which then sucks more steam through the turbine here as it condenses. And then that liquid is pumped back to the boiler where it's boiled, and then the process continues. Now, the second law, we don't have time to go into the details in this course. In the next course, we will talk a little bit about this. But the second law of thermodynamics tells us that there is a fundamental physical limit to the efficiency of this, and it doesn't matter on what the materials are or the fluids. If you use a different kind of fluid other than water, or you use a special material in the turbine, or you have a super efficient condenser, none of that matters in the ultimate efficiency of the system. It just, let's see, this is what a turbine looks like, just to give you an idea. What matters is the temperature at which you put heat into the system and the temperature that you reject heat out of the system. The efficiency is a very simple mathematical relationship of those temperatures, and it's the hot temperature minus the cold temperature divided by the hot temperature times 100. And typically, the hot temperature is 360 to 500 degrees Fahrenheit, and the cool temperature is, basically you can't get much cooler than the Earth's atmosphere or the temperature of the Earth, and that's 60 to 100 degrees typically. And the temperatures you need to use when you calculate the efficiency are what are called absolute temperatures in relation to absolute zero. So in the Fahrenheit system, it's the Fahrenheit temperature plus 460. So if you plug these numbers in, then you get a maximum efficiency of about 37%. And then that's the efficiency that you could possibly hope for. You have some inefficiency in the turbine and in the condenser and various other things, as well as the fundamental theoretical limit. So you can only approach that. And so typically a coal-fired power plant will put 1/3 of its energy of the coal into the electricity that comes out of the system, and 2/3 of the energy is turned into waste heat that's just thrown away right at the power plant. So the coal-fired power plant throws away twice as much energy as it actually sells, and it throws it away right at the power plant. That's why big coal, oil, nuclear power plants are located far from where people live, because they need to get rid of that heat. People don't want to live next to these big systems. Another system you could use here, a thermal system, is what's called ocean thermal energy conversion. So that anytime you have two differences in temperature, you can create energy. You can create a flow of energy. You can create power. And so anytime you have two differences in general in nature, so if you have a difference in elevation, like water falls from a high elevation to a low elevation, you can extract energy. Temperature difference, high temperature to a low temperature, you can extract useful energy. A chemical concentrations, changing chemical energy from one to another, you can extract useful energy. So in this case, we're using the temperature of the surface of the ocean, let's say in the tropics, let's say around Hawaii. At the surface, it's quite warm, maybe 80, 85 degrees. But at 100, 150, 200 feet deep in the ocean, it might be 40 or 50 degrees. And so you can use this temperature differential to boil a fluid like ammonia that boils at a low temperature. It boils like at maybe 70, 75 degrees, 60 degrees, depending on the pressure that it's under. And then that ammonia steam can run through a turbine just like water steam would. Then you'd condense it in the cool depths of the ocean, and then that would be a liquid that then you would pump back up, and it would go through this whole process again. And if you look at the typical efficiencies you might use, you might find in the ocean, you'd get maybe 6 or 7 or 8 or 10% efficiency, which doesn't sound like very much. But then again, the fuel is free. And so if you can build these components cheap enough, then it doesn't really matter what the efficiency is. And that's one thing I want to point out is it's you got to be careful about saying, well, I don't want to use a renewable energy system because it's so incredibly inefficient, but all you're wasting is sunlight or wind or something like that. If you can make the equipment cheap enough, then even low efficiencies can be quite practical. And there's actually a system like this that operates in Hawaii. So let's summarize. The second law, as energy changes form, it loses usefulness. Energy flows from more concentrated forms to less concentrated forms. This gives a direction to change and has been called time zero. And again, things change in the form of being from more concentrated to less concentrated. Energy is not lost when energy is transformed, but entropy goes up, and meaning that there's less usefulness to the energy. And the energy can no longer do the same quality of work. It loses usefulness. So in meditation, the mind spontaneously flows from more concrete to less concrete forms of the mantra until the mantra disappears and we are left with being. We just take the correct angle and the process is automatic from there. Meditation offsets the effects of entropy on the mind and the physiology. And now we've talked a lot about the second law of thermodynamics. And there's a third law that's not going to really affect our discussion of renewable energy very much, but it says that the entropy, the orderliness of the concentration of energy in a substance approaches zero as its temperature approaches absolute zero. At absolute zero, everything stops. So in a sort of tongue-in-cheek way, somebody made this statement of the laws of thermodynamics. The first law saying you can't win, you can't create energy. The second law, you can't break even. There's always some unrecoverable loss in energy transformation. And the third one says you can't get out of the game. Processes stop at absolute zero. So you can't win, you can't break even, and you can't get out of the game. That's the kind of cynical version of the laws of thermodynamics. So another consequence of the second law of thermodynamics is that not all energy has the same usefulness. So what that says is we want to match the source of energy to the end use of energy. If we have a source of energy that's very highly orderly, can do many different things, we want to use it for those things that are that require that kind of highly orderly energy. And if we have an end use that doesn't require highly orderly energy, like low temperature heat, everything eventually turns to low temperature heat that can no longer be used by the system, then we want to try to match that source. So, for example, if you have 1 kilowatt of electrical energy, it has the ability to do a lot of different kinds of work. It can run light bulbs, it can run electronics, it can run motors. But if you have 1 kilowatt of 70-degree heat in a system that's at 70 degrees, it's really not useful to you at all, even though it's the same amount of energy. So we'd want to, anytime we have to make heat, it's better not to use electricity or high quality forms of energy, because we can make heat just with friction and various other ways. So again, summarize the third law. At absolute zero, entropy approaches zero and everything stops. In the unified field, the absolute entropy is zero, order is perfect, and all activity ceases. So let's take a look at what the Simpsons have to say about thermodynamics.
I'm worried about the kids, homie. Lisa's becoming very obsessive. This morning, I caught her trying to dissect her own raincoat.
I know. And this perpetual motion machine she made today is a joke. It just keeps going faster and faster.
And Bart isn't doing very well either. He needs boundaries and structure. There's something about flying a kite at night that's so unwholesome.
Hello, Mother dear.
Oh, that's it. We have to get them back to school.
I'm with you, Marge. Lisa, get in here. In this house, we obey the laws of thermodynamics.
Thanks, and tomorrow we'll do some calculations that will help make these abstract ideas about thermodynamics a little bit more concrete.